Mr. Paley. Wait, you're not Mr. Haas. Who are you?
I am Mr. Paley.
I guess I just said that.
Hello, in Mathland, wherever you're watching this. So today's video is hopefully going to get you a better sense of what a derivative is really trying to measure. So when you think derivative, hopefully a word pops into your brain. Slow. Or change, right? So let me throw this out there. Let me sketch maybe a quick little graph called f of x.
Beautiful.
And this could be, it could be as basic as, a roller coaster looks like this, or maybe this function is describing at some time you have some amount of money, and your amount of monies are changing, some business application, physics. It could be a variety of applications, but I believe for this video, we'll just kind of generally call it a function, what it represents, anything you want.
Make it up.
Make it. And what calculus is going to try to do is measure an instant change, which by itself is kind of strange because a change is implying you have two things to compare. So what if we wanted to know how is the function changing at that instant, right? At that specific x value? Again, whether it be time or distance or whatever the application may be. Well, you can't measure a change from one thing.
Yeah, that's like taking a photograph and saying, how fast are you moving in this photo?
Yeah,
that's crazy.
It's still, right? It's one thing, it's one piece of information. So, let us calculate an average change.
That's good.
So we have this x value, which would then, if we wanted to figure out its value, would be f of x. Okay? It would be the output at that specific x value. And I guess then we could take some other x value, maybe over here, that x value plus 1, right? We'll move 1 to the right. And that would get us a new value, f of x plus 1.
Very nice.
And we can certainly measure the change between those two values. Okay? I would calculate the slope. So I have slope, which is a change in y values divided by a change in x values. And in this case, these are your y values, right? When you use the function, you get the y value. So we have whatever the function value is at that x value minus the function value at our original.
So you're saying function values, so those are like your outputs.
Yeah.
So when I plug in x plus 1 into the function, I'm getting out f of x plus 1.
That's right.
That's
Like
the
if-
y value, right?
If for some reason this was f of x squared, then I guess we're just squaring that. If it's cubed,
Got it.
it's
Got
whatever
it.
the function's defined as exactly.
Fantastic.
Yep. So we have our change in y values. We want to divide that by the slight change in x values. So we have x plus 1 minus x.
Beautiful.
And that will get us, basically visually, the slope of the line between those 2 points. And that's called the average rate of change. But that's not what we want.
Ah, we want the instantaneous rate of change.
Instant rate of change. And here's where it gets a little abstract, but you could probably stay with me. Why did I move 1 to the right? Right? Why don't I move a half a unit in? Half a unit in. A half a unit in.
Ooh, I like it.
And now these 2 points are closer together.
And there would be a half in the denominator too, right?
Like
Yeah.
And so these 2 points are visually getting closer together. These get closer together. This average rate of change is a little more aligned with the instant rate of change.
I see where you're going with this, Paley. Very
Well, why
clever.
add a half? Why not add a third, a fifth, an eighth,
A millionth.
a millionth?
A Google-eth.
Right. What it's all about is picking a point that's infinitely close to our original value. Remember, we want the instant change at that spot.
Right.
So we know we need 2 points because we're measuring a change. Let me erase some of what I have here. So what we do is we pick our second point as x plus tiny bit.
Tiny bit.
That's that millionth or trillionth or googleth, right? That tiny bit,
Very nice.
which mathematicians call h.
Yeah. So
And now-
h is representing that tiny bit that you're adding to x.
That's right. So if we're at 3, we'll go to 3.00000000001.
Beautiful.
If we're at 10, we'll go to 10.0000000.
Got it.
We could also be on the left side of the original.
Sure.
Then it would be x minus h.
Right.
Should still work. But to keep things positive, we'll just go to this side. Which then gives us f of x plus h. And we'll play the same game with slope.
So that's your y, or your output when your input is x plus h, and your output when your input is x. Beautiful.
And that might look a lot like
X
plus h minus another x, of course.
Very good.
So it's the change in y's divided by the change in x's. But we need to somehow communicate that that h is as small as we can possibly make it.
You basically want it to be 0, but it can't really be 0 because then
We'd
it's
be-
the same point.
We'd be exactly at the same spot. And here's where we introduce this idea of a limit as that h value approaches 0. Thereby
There
we
we
have the slope between 2 points,
Right?
and this verifies that those 2 points are getting infinitely close together, which changes the picture ever so slightly.
So instead of having a secant line and finding the average slope, you're getting really infinitely close to a tangent line at that point and an instantaneous rate of change.
Beautiful thing, isn't it?
That is, I mean, calculus is amazing.
It is amazing. And it's this limit as h approaches 0 that's forcing these 2 points to be infinitely close.
Right.
So that's the limit definition of a derivative, right? Derivatives measure slope, they measure change. That's what this is measuring, forcing the 2 points to be infinitely close. So you should understand, I hope, why the average rate of change turns to an instant rate of change when those 2 points get infinitely close.
Beautiful.
And now we're going to just go through some basic algebraic manipulations of that concept.
Fantastic. Thank you, Mr. Paley. I almost said thank you, Mr. Haas.